This is a continuation of our introduction to sequences in 13.1. We have a couple more ideas to talk about. We're going to talk about recursively defined sequences. To calculate the nth term of a recursively defined sequence, we need to know the value of the preceding term. The preceding term would be the n minus 1th term, or n minus 1st term, I guess you might say. So let's look at an example of a recursively defined sequence. And as we go through the example, we'll talk more about what this word recursively actually means. So we want to write out the first 6 terms of a sequence defined in the following way. We say a sub 1 is 3, but then we have another statement, a sub n equals 2n minus a sub n minus 1. So this is our definition, our recursive definition of a sequence. Now let's see what it means to write out the first 6 terms. The first term, there's nothing to figure out. They're telling us what the first term is, and that's pretty typical with a recursive definition. We're told the first term is 3. A sub 1 is 3. Okay. Now, suppose we want to figure out what a sub 2 is. For a sub 2 or any succeeding term, we have to use this formula on the right, the a sub n formula. So I'm going to plug in 2 for n. So on the right-hand side, I would get 2 times 2 minus a sub 2 minus 1, putting 2 in place of n. What does this mean? This means 2 times 2 is 4 minus a sub 2 minus 1 is a sub 1. And so to figure out what a sub 2 is, I have to take 4 minus a sub 1, which is 3. We're told that up above. 4 minus 3 is 1. And so a sub 2 is 1. Now let's do a sub 3. A sub 3 we also compute from the a sub n formula. That's 2 times 3, because n is now 3, minus a sub 3 minus 1. 2 times 3 is 6 minus a sub 2. So notice to get a sub 3, we need to have a value for a sub 2, which is what we just figured out. And this is really what recursively defined sequences is all about. To get a sub 3, to compute a value for a sub 3, we need to already have the value for a sub 2, and we do now. So we can write 6 minus 1 is 5. We got a sub 3. And now let's go with a sub 4. A sub 4, using the formula, is 2 times 4 minus a sub 4 minus 1. 2 times 4 is 8 minus a sub 3. So to get a sub 4, we need to know what a sub 3 is, which is what we just figured out. So that's 8 minus 5. 8 minus 5 is 3. A sub 4 is 3. And I think we got a couple more we got to do here, right? We need 6 terms, so we need a sub 5 is going back to the a sub n formula. 2 times 5 minus a sub 5 minus 1 is 10 minus a sub 4, or 10 minus what we just figured out for the preceding term. 10 minus 3 is 7. And finally, we need a 6th term. We need a sub 6 is 2 times 6 minus a sub 6 minus 1 is 12 minus a sub 5, which is 12 minus the term we just figured out, 7. 12 minus 7 is going to be 5. And we can go on and on. But to get any term, like I can't jump out to a sub 100. If I wanted to know a sub 100, I would have to first figure out what a sub 99 is. You always need the term coming before you get the next term with a recursively defined sequence. So there we got just an example in plugging in some values here, figuring out the first few terms. We got one more thing to talk about in this introduction. We're going to talk a little bit about the famous Fibonacci sequence, which is given by this list of numbers, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, so on and so forth. Now, it's maybe not obvious at first glance what the pattern is, but once you see the pattern, it is a very simple idea. So start out with two ones. So start out with 1 and 1. I'm going to add the ones together to get the next term. 1 plus 1 is 2. Then I'm going to add this 1 and this 2 together to get the next term. 1 plus 2 is 3. Then I'm going to add 2 plus 3 together to get 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21, so on and so forth. That's the pattern of the Fibonacci sequence. To get any one term that you look at, like 8, is the sum of the two preceding terms. 3 plus 5 is 8. Any one term like 34 is the sum of the two preceding terms. 13 plus 21 is 34. So I guess we could kind of write out the pattern by saying 1 plus 1 is 2. Then this 1 plus that 2 gives me 3 the next term. This 2 plus that 3 gives me 5. The 3 plus the 5 term gives me the 8. The 5 plus the 8 term gives me the 13. The 8 plus the 13 gives me the 21. The 13 plus the 21 is going to give me the 34 term, and so on and so forth. All right. Now, the Fibonacci sequence actually has lots of applications. It comes up a lot in biology because it's a certain natural kind of pattern. It's a growth pattern in some plants and animals. And we're not really going to work with it too much more, but I want you to have seen the recursive formula, the recursive definition for the Fibonacci sequence, which looks like what's in the box here. And it's got a sub 1 equals 1, a sub 2 equals 1. We actually are given the first two terms of the sequence, and this a sub n formula tells us how to get beyond the first two terms. A sub n is a sub n minus 1 plus a sub n minus 2. Okay, now it's, the Fibonacci sequence is a fairly simple idea, and this recursive definition in the box should seem a little bit like, whoa, how'd they come up with that? So let's just write out a few terms using this formula so we can see how this formula relates to the Fibonacci sequence that we have above. So a sub 1 is 1, we're just given that. A sub 2 is 1, we're just given that. A sub 3 we get by plugging into the a sub n formula. So a sub 3 is a sub 3 minus 1 plus a sub 3 minus 2. So I put 3 in place of n in this formula. That means a sub 3 is a sub 2 plus a sub 1. So notice that formula is a way of expressing this idea of adding the two preceding terms, which we're copying from up above here, is just 1 plus 1. So a sub 3 is 2. How would we calculate a sub 4? Using the recursion formula, that's a sub 4 minus 1 plus a sub 4 minus 2 is a sub 3 plus a sub 2. A sub 3 we just figured out was the number 2. A sub 2 was the 1 from up above. 2 plus 1 is 3. So I know it's kind of like a lot of formula just to get a fairly simple pattern, isn't it? It's interesting that the notation is so complicated. Let's write one more. A sub 5 is a sub 5 minus 1 plus a sub 5 minus 2. A sub 4 plus a sub 3. A sub 4 we just calculated down here is 3. A sub 3 was 2. 3 plus 2 is 5. So that gave us that fifth term of the Fibonacci sequence. So far we got 1, 1, 2, 3, 5. The next one is one more. I'm going to write out a sub 6. Now, try to see the whole point of this strange looking formula is it just ends up being that a sub 6 is going to be a sub 5 plus a sub 4 if we plug into the formula, right? I'm leaving out the step I've been writing up above for the previous one. So a sub 5 is 5, a sub 4 is 3, 5 plus 3 is 8. There's my term 8. So this is just an exercise in getting used to the look and being able to write out terms from a recursive formula, in this case for the famous Fibonacci sequence that we started out at the top of the page here.